This is the video for the Bowlero problem. These are what we'll be using. What I'll be using to solve for VO2, VO3, and angular velocity, along with the force David puts onto the ball. So, for starters, in the first image, the energy that's being given off is gravitational and kinetic linear energy. And how we'll write that is we'll actually separate that evenly between three each. And so, in the next image, the ball is at the ground. So in this case, there's only linear kinetic energy, no gravitational energy, because the ball is not being held up top and walking, but now it is on the ground walking.
The height is like the colors. 1 meter.
And so this one would be 6, so it has to equal to the same amount as the last image. And in this instance, there is no gravitational, but there's still kinetic energy linearly and rotationally this time. So now it will split again evenly. And these are the graphs we have so far. Now, in order to solve for this one, we have to set an equation where these two energies equal to the linear kinetic energy of event 2. So, this one will be using red.
So for VO3, because you already have VO2 equals to 4.6 meters per second. Then you can use the second equation, which is
Now let's see if this is still recording.
equals to VO3 plus
Let's see. All right. So this is how we'll solve it. EG1 has the formula of mgh plus the formula for kinetic energy linearly. 1/2
W is gravitational. Circular.
For this, I'll just be saying 1 because we know that this is the linear equation for kinetic energy. So I won't be putting L1, but I'll be putting a 1 to say that that is the energy for the first bar. And this is all equal to the kinetic linear energy of event 2.
I'm looking at
Now, starters, multiply both sides of 2. Canceling out the 1/2, making mgh
all I did was plug in value.
multiplied by 2.
But you combine them.
And then we'll divide both sides by m to cancel out the m's.
And then you combine them by taking out m.
Yeah, because they both have mass, so I'm just
Yeah.
So it's going to be 1/2 times.
So I just wait.
Square.
And then we'll square root both sides to get rid of that
3 squared
squared up here.
plus 1/2
So then
times
our equation would be
W is
2 times the gravity. In this case, we'll just round up to 10, multiplied by the height, which is 1 meter, plus the linear velocity of event 1, which is just 1 meter
You
per
told me I
second.
did that second part wrong.
You did.
I did. I looked at it and
And now for the math. So, total this up, we know that this is just 21, so we'll square root of 21.
So it's like 7 times.
which is 4.58. Go around that to 4.6.
So actually, in fact, with the VLP square, so inside I'm gonna have the 1/2 mass plus
So that is the equation
I
for this one right here.
Hold on, freaking me out.
square.
And now, setting up the equation. We include this time.
The square root of
And then
1/2 mass
for that, we're going to set
divided by
kinetic linear energy of event 2 equal to the kinetic linear energy of event 3 and kinetic rotational energy of event 3.
Do you know these pre-made?
Everything.
Which like the graph, equations and what we're getting?
When David was first I set up all like because I already know the formulas.
See if that's still review. Alrighty, so that is. So, same process as the first one. We'll plug in the equations and then solve for an equation to get the variable we're looking for. In this case, I want to look for VO3, and I'll show you that process.
be approximately 3.9 meters per second. So that's gonna be my VO. And to find circular velocity, it's just gonna be equals to VL3 divided by R.
Multiply both sides by 2,
3.9.
cancel out the 1/2. Now we're left with
11.
this.
That's gonna be approximate to 35.
Now, in order to set this equal to where we don't have the inertia or the angular velocity, we use these equations right here. So we have angular velocity is equal to linear velocity divided by the radius, and then inertia. In this case, the inertia of the ball is a sphere. So the equation for that would be 2 divided by 5 or 2/5 multiplied by mass times radius squared. So we'll go plugging in those.
Which is the weight. We want to find this one. So according to Newton's second law, we have total force equals to mass times AC. AC times stands for centrifugal acceleration because you are going in a circular motion. So total force, we have of dg, subtract the force of the ball. This is the opposite.
So opposite side here, we could say that V3
equals to mass times we
if
have
that's squared, V3 divided by R if
V
that's
squared
squared. This would be
divided
the
by the
same.
radius of your.
And so in this case, the R's, or the R2s cancel out.
Mass times gravity. Mass of the ball. Subtract by the mass times V squared over R.
This
So
equation.
it's going to be mass times.
And then
V
same again,
minus
we will
V in this case is VO2.
divide both sides by M.
Divided by R. And substitute the number in, it's going to be
To take,
5
to get rid of the M.
times 10 minus 4.
So we're left with V2 squared equals V, so we know V3 squared plus 2/5 V3 squared is just 7/5, which can be simplified to 1/4.
So it's going to be 5 times 10 plus 4. And you will have, it's approximately 150, right?
Divide both sides by 1/4.
That's right. So that's how you solve the goal.
And then we could split this, up, so it could be 1/5, or 1 divided by 1/4 multiplied by velocity of event 2 squared. And then we'll square root both sides to get this equation right here. And then you know square root and the know a square root and a value like r, or in this case v, the square root cancel out with the square root, so then it would just be this times v2.
What?
Now it's just plugging in numbers. So v3 equals
Radians, what?
times v2, which was 4.6, what we solved earlier, which we get 3.88, but in this case we say 3.9.
I almost forgot about that. What was it? I have to put like meters per second.
So that's what we got. Now, plug this back in right here.
Remember our math teacher told us like degrees means it's usually
Now we're going to solve for the angular velocity. Angular velocity is super simple. We already know that the radius is 0.11 meters, and then since this is event 3, we'll use the velocity of event 3, so 3.9
they own up each other solve but
second divided by,
You're gonna wait just to get him?
the answer for that will be radians per second. So 3.9 divided by
Oh my
0.11,
gosh, this is just CSE.
35.45.
Really? Yeah. David,
See this? This is just this
Radians.
Imagine.
I don't think it's easy to
Is
see.
it just discrete?
Maybe. I don't know.
I don't think he does. I think he does.
So here I'll be solving the Bowlero problem. So here are the givens that we have. So the first thing we'll do is construct the energy charts. So at first he's holding the ball like this. So there's two types of energy involved here. First there's the gravitational potential energy of the ball. And it says that the ball has an initial velocity of 1 meter per second. So the ball will have an initial kinetic energy. So at first there's two.
So these are the equations. So these are the numbers that I found for
And then
all the unknowns. We're now going into the
all of that
force.
gravitational potential energy is converted to kinetic energy and added on to the initial kinetic energy. So for our second portion, we're going to have a long bar. The sum of these two energies converts to kinetic energy. And our third chart will be the event at which the ball hits the ground and starts rolling.
Ball,
When that happens,
force on the ball.
this kinetic energy is converted
So for this one, we'll use the equation.
Oh, so here, this is just going to be a thin technique of the ball that it gets. When it hits the ground, it starts rolling. So that energy splits off and then rotation.
Since the ball is going in a circular motion,
These to set up
right?
equations. The first equation we
we
have
use the
is
centripetal acceleration.
the sum of these two energies is equal to
And then
this.
that could be described as, so this is how I'm getting ahead of myself. So we'll say that the sum of centripetal force is force of David minus the force of the earth on the ball equal to m times this. But the equation for centripetal acceleration is actually, in this case, we use VL2 because that's when the ball is coming here. So we'll use that one.
Somebody missing a black earpiece.
Squared times capital R. In this case, capital R represents the circular radius. And since we know that the ball initially starts at 1, and it comes down to here, and this is the pivot, the height is equal to the circular radius, so which equals to 1 meter.
I gave a like explain. I gave.
But in order to find the force, David, on the ball,
So basically, like,
we'll add force of the earth to the ball to both
this
sides.
problem is just dealing with understanding how to find angular and linear velocity, and then the forces on how.
And then we know that the earth on the ball, which is the mg,
How it's circulated.
is this.
And so like, is that what you're kind of trying to ask? Is like,
Well, when I draw these graphs,
how would you explain it?
And then we'll take out the m from both equations.
He's at delivering solve.
I'll do it in photo.
It's just the transfer process.
So now we can plug in.
So you can square root both sides.
Let's go.
So the mass would be 5 kilograms, because that's the mass of the ball, multiplied by gravity, which we'll round to 10 for this one, like we did before. And then we found the velocity from earlier, which would be 4.6 meters per second squared.
First you have EK,
This class makes fun of kids.
which is gonna be.
Divided by 1 meter.
So,
There's math on that. 5 multiplied by 10 plus 4.6 divided by 1.
Yeah, the one
And if I had the
155.8 newtons. So this has been the Bowlero equation and problem, or the Bowlero problem, sorry. And this one we found the velocity, the linear velocity of event 2 to be 4.6 meters per second. We found the linear velocity for event 3 to be 8.9 meters per second. The angular velocity for event 3 to be 35.45 radians per second. And then the force from David onto the ball being 155.8 newtons.